Okay, well, it says I'm recording. That's good. Okay, so welcome to my live tutorial of 4NEC2. Get rid of that thing and get rid of my little picture in the lower right hand corner. Yeah, that did it. Okay. Alright, so hopefully you've already seen this page and maybe downloaded the software. I'll paste the link into the chat thing. Just in case anyone has not downloaded it yet. So of course the first thing we do is start the program, and it looks like this. Okay, so here's what, I'll just close these for now. This thing is called the main window. You don't really set anything in this. It's mostly here to just display information. I don't even think you can. No, you can't change the file name there. This is all pretty much just read-only information about the file you have loaded. Now what we're going to do is start a new document or a new NEC file and just create an antenna from scratch. So the way we do that is not like you would think there would be a new option up here in file in the main window, but that's not how it works. What we have to do is edit input file, and this thing under settings here where it says notepad editor, NEC editor, geometry edit, NEC editor new, these are different editors you can switch between. The thing you usually want to use is this NEC editor new, but if we pick one of these other editors, then it's going to load the file, or if any, into say like notepad or something, because it is just a text file. So what we do is edit input file. We've already got something in here, so now we have a file menu under this editor, and we do new to get a brand new empty file. So once we've got an empty file, notice that we've got several tabs here. We want to, first thing I want to do is go through the tabs and set all the stuff that like that we're going to need, like frequency and unit sizes and stuff like that. One thing is this comment, so I'm just going to put a comment in here that says I think we're going to just do a 2 meter dipole. So I'm going to type in 2 meter dipole for tutorial purposes. And then I'm going to go through these other tabs and we'll set various settings before we do anything else. So let's see, the first tab's the symbols tab. I'll tell you what symbols are later, but for now the only thing we care about is this thing at the bottom here that says scaling. And notice we have meters, feet, inches, and wavelength, or custom, which lets you set in, this would be the fraction or multiple of a meter that your units are. So if you wanted to use cubits or something, I guess you could figure out what that was and type it in, but we're just going to use meters since that's the easiest way to relate our wavelength to the length of the antenna and stuff like that. You might, if you wanted to use imperial units, you might want to use feet or inches depending on the size of the antenna. So alright, so meters is set, that's good. We don't have anything to set under geometry yet. Source load, we don't have anything we need to do there. Frequency ground, so what I'm going to type in for frequency here is 146 megahertz will be our target frequency for doing plots and things that require a frequency. The other thing I'm going to do is this environment. Notice we have ground and free space. I'm going to start out just doing a free space, and then later I'll turn on the ground and show you how to do that stuff. So I'm going to set environment to free space, which then grays out all of this other stuff that has to do with grounds and things. So let's see, what else do we have? You always want this use extended kernel thing turned on, and the rest of this we don't really need. So that's pretty much all we have to do to start with. And I did put this as in there as a comment. So now I'll just go ahead and save this as, let's see, 2 meter tutorial.nec. Okay, so now what we're going to do is, let's see, window geometry. Now we're going to actually create the wire for the dipole. Now this is a geometry window. We're in free space, so it's not showing a plane at the bottom or anything representing the ground. And we're going to create a wire that's going up from the Z and down from the Z, so it's centered on this 0, 0, 0 point. So the way we do that is we go to geometry. Now we've got these like spreadsheet row things here. So we'll do type wire. There's other types under here, but I'll kind of get to those later. A lot of these are kind of complicated, and most of the time you're going to be using wire, or maybe like copy, move, or rotate, or something like that. But wire is the main simple one. Okay, so wire has these fields we need to fill out. Tag is just a number. You can assign any number you want, so you can assign like tag. I just usually start numbering them at 1, so this wire is going to be tag 1. Then segs is the number of segments we have. For now I'm going to type in 19. We want an odd number of segments, and there's a reason why we want an odd number of segments, but I'll get into that later. Okay, so now we need to type a starting XYZ coordinate and an ending XYZ coordinate. And notice what happens here if I put in like -1, -1, -1 here, and +1, +1, +1 here, and oh, this is the radius of the wire. There happen to be some symbolic constants we can use, so I'm going to put in this. If you put in like #20, will resolve to however many millimeters radius a 20 gauge wire is. But anyway, this is not the wire we want yet. I just want to show you what's going to happen here. So when we click on this, it'll actually update, and then we'll see. We'll actually get a wire going from, we seem to be zoomed way in here. There we go. Okay. Use page up and page down to zoom. So this is what it looks like when we've got a wire going from -1, 1, 1 to +1, 1, 1. So you kind of get the idea of what's going on here. You're going to have to think in like three-dimensional graph paper terms. But this is not what we want. So what we do want is we want a wire going down through the X and then back up through the, down from we want a wire that's at 0, 0 for X and Y. So 0, 0. And then for Z, because we want a 2 meter antenna, we're going to do -0.5 meters, because that's 1/4 of the 2 meter wavelength. Now you may be saying, well, wait, it's not really 1/4 of a wavelength, blah, 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 because of velocity factor and stuff like that. But for now, we're just going to pretend that this is like some kind of perfect conductor that'll conduct at the speed of light in a vacuum, and then we'll fix it later. That's where the optimizer can help us out, though it's a little more useful for other stuff. Okay, so the second point, the first point is going to be -0.5, and then the second point is going to be +0.5. And then our radius is 20 gauge, is whatever the radius of a 20 gauge wire is. So now when we click on this again, we're actually going to get a wire going vertically. Now there's some things up here we can do. Show segments that'll show a little circle in the middle of every segment to give you an idea how many. Actually, I guess it's not in the middle. I guess that's the dividing line of each segment. We can also do show. Let's see, I thought we had show segment numbers. We've only got show tag numbers, but if we do show tag number, it's going to put a little number 1 next to this wire. So if we had lots of wires or something, that might help us out a little bit, but doesn't really do us any good. Okay. So now you may be saying, but wait, don't we need 2 wires because a dipole actually consists of 2 wires? You may be thinking that this looks like a monopole, but you'll see what we're going to do here in a second when I add the voltage source. So because we have 19 segments, it should be segment 10 that's right in the middle, and that's what we want to be our feed point. So I go over to this source load tab, and for type of and under source, notice we have sources and loads. Under source, I'm going to tell it we want a voltage source. The tag of the wire we want the voltage source on is 1, because I named it, or I labeled it tag 1 over here. The segment we want is 10, because we want it to be right in the middle. And then this other stuff is kind of optional and we don't really need it. This will inject whatever our frequency is at this point, and we can just ignore. We don't have to specify a real or imaginary voltage. We don't have to specify phase if we don't want. This would come, like phase would come in useful if you wanted to have like an active phased array or something. But in this case it's a simple dipole, so we don't need to worry about all this stuff right now. Okay, so notice over here we get this bigger circle that indicates our voltage source in the middle there. And what this actually it does is it actually causes it sort of causes a magical injection of voltage right here that's just gonna oscillate back and forth like this. So in reality, this would of course have to be cut, and then we'd have a feed, like a feed line coming in with 2 leads. But the way it works in the modeling program is we just have one complete segment, and this segment is just set up to magically start oscillating up and down like this. So because we're not dealing with real world, we're not having to deal with limitations of the real world. We can actually just like inject a voltage right here, and that's it. Now we don't have any loads, so this wire is going to be a perfect conductor right now. But I'll get to the other fancy stuff later, because I'm going to get into some stuff that's going to make a lot of this a little bit easier. It's going to make some things more realistic and easier. So we've got, and that's where symbols come in, but right now we're not using those. So this is how we create a wire. This is how we create a voltage source on the wire. We've got our voltage source in the middle of the wire, and our wire is approximately the right length. And our target frequency is 146. So I'm going to go up here. Notice this says file change, so I'm going to go up here and do save. Now we actually want to try to calculate something. So now we want to see, like, what is this wire going to do? The way you do that is calculate NEC output data. And when you do this, you'll get a little dialog thing that comes up here. Use original file. If you edit the file with a text editor, you can actually insert commands to calculate different things, but I pretty much never do that. I usually select stuff down here. So we've got far field pattern. That'll give us the interesting diagram of the radiation pattern of the antenna. And notice there's a frequency which should default to the one that we put in the file. And then there's frequency sweep, which is going to do something similar to an antenna analyzer or a VNA. We can give it a start and stop frequency, which I have it set up for like HF antennas right now. But let's try, let's see, let's just do like 140 to 150 step 0.1. So this should like run the calculations for each of these frequencies from 140 to 150, incrementing 0.1 each time, and we'll get some nice graphs of like SWR and stuff like that. Now notice there's some other things here. Near field pattern is not terribly useful for radio. I guess if you we're doing some kind of RFID thing or something, maybe that would be useful, but I've never really used that. This its HF gain table and its HF gain at 30 frequencies, these are outputs that can be loaded into another program called its HF, which I don't have installed right now and I'm not going to cover today, but this is like a propagation modeling program where you could conceivably like define your antenna in here and then have the thing generate some output data showing what your antenna gain pattern looks like, and then use this its HF program to tell you, you know, what sort of signal propagation across the map you were going to get for different frequencies and different like wattages and stuff like that. So anyway, so what we're going to do is frequency sweep. We're going to do from 140 to 150 with 0.1, 140 to 150 megahertz. This is all megahertz in 0.1 megahertz increments. And this forward-backward thing, this is just, for our purposes, this isn't going to help us very much. This is if you wanted to calculate like front-to-back ratio and things like that. You can define what angle you want to use. So like theta is on the XY plane, I believe. Let's just set this to 90. Phi is like the inclination or whatever you call it, so that's on the like YZ or XZ plane. I'll just do 0. And then backward and 90, negative 90, whatever. I don't even usually bother with those on a lot of stuff. So generate. Now we're going to get, I thought I killed that. Anyway, okay. So it loads up because NEC2 is actually a separate program that was kind of originally designed as a batch process. So what it's doing is it's actually generating, it's doing some pre-processing on the data that we've defined, or the NEC file we've defined, and then it's running another program on it, so it loads up that thing. Let me kill this conemu here just to keep that from popping up. So you can see here we've got an SWR graph, and it'll tell us like, alright, so if we actually were to construct this antenna perfectly with a perfect conductor that doesn't exist, then we would get an SWR under 2 for pretty much this whole range. And for like 146, notice that's not actually perfect because the wavelength for 146 megahertz is actually a little bit longer than 2 meters. So, but we're going to get more complicated in a second and add and turn this wire into a copper wire instead of a perfect conductor. So there's some other things here. Gain front to back. This for dipole, this isn't very interesting. This would be more interesting if we had a Yagi. And here's the impedance thing. So R ohms. This is telling us right now our impedance would be about 75 ohms real, and the reactance would be about 13 ohms, positive 13 ohms. So this thing would actually be at 146 anyway. It would actually be a little bit inductive. And then over here at the place where it matches up better where it's actually resonant is, you know, actually like 144.5 or something like that. Anyway, so this is the nice stuff you get when you do a frequency sweep. You can generate these graphs like this, and the thing also happened to calculate a far field pattern over here. This is the vertical plane, so this is like the YZ plane or whatever. Then you can also drag on this and see what the gain is at different angles. Yeah, so anyway, it's pretty much what we expect. 2.1 dB forward and almost 0 if it's, yeah, well, absolute 0. Well, actually it says negative 1000 dB if it's straight up, but anyway, whatever. Pretty much that's exactly what we would expect. And if we turn off this thing that says vertical plane, then, oh, okay, so because we did a frequency sweep, only the horizontal plane was generated, but in a second we'll generate both of them and make a little 3D thing. We can still, even though we only have one plane, we can also go to this window 3D viewer and bring up the thing in this 3D viewer, and then if we go over here where it says hide pattern and tell it to show the pattern, then we'll get that's kind of weird that maybe that one doesn't work too well. There we go. Then we'll get, like, because this, we're only getting a slice because we only told it to generate vertical for a frequency sweep. Anyway, we'll make this look better in a second. Okay, so now here's the other thing. I'll just run this real quick so we can look at it. NEC output data, and we'll tell it far field pattern at 146, and instead of vertical or horizontal we'll do full, which will do both of them. And there's some other options down here I'm not really all that familiar with, like I guess surface wave would tell us something about the propagation as a surface wave, but we don't even have a ground in here. I'm not even sure what run average gain test is, but we can check. You could actually check to see what the strength of the electrical field would be at a certain distance in kilometers if you want. That could be useful in some cases, though the way we've specified our voltage source, I think we end up with, because we didn't really specify anything and it defaults to 1, I think we're going to end up with like 5 watts of power as our amount of power, so I don't know how much good that does, though I don't know, most HTs are like 5 watts. So anyway, this is pretty much all you have to do to get the far field pattern. Just do far field pattern. So it's calculate NEC data, this thing pops up, far field pattern, make sure your frequency is the frequency you want, full, and then hit generate. Oh man, that Connie MU keeps popping up even though I quit it. Okay, so now we can show both. So this is what it looks like from the top, is just a big circle. And then if we do vertical plane from the side, this is a cross section of the donut. And we can also do show both horizontal and vertical, and it'll put them both on there at one time. And when we do show both, it'll actually add a wireframe to the geometry editor. It's just I don't find that very useful because this is too limited. So let's see what it looks like in the 3D viewer. Window, 3D viewer. I don't know why this always defaults to being hidden, but alright, so I'm changing hide pattern to multicolor, and now we'll get a nice rainbow donut here showing us the radiation pattern. There's a few other things here like transparent. It shows you like a red transparent piece. Yeah, so that's how you actually get this interesting thing here. This will get more interesting once we add a ground. Right now it just looks like a donut floating in space, but let's cover some other stuff first here. Okay, so one thing is it's not really ideal to hard code values into here, and for that reason we have what are called symbols. So let's define a symbol called length. I'll just say len equals 1, and our units are meters, so that's 1 meter. So this is length of dipole. Now, instead of hard coding this stuff under geometry, I'm going to change the negative 0.5 to negative len divided by 2, and then the positive z 0.5, I'm going to change that to len divided by 2. We can do little math expressions on this stuff, and we can define our coordinates based on whatever we set those variables to over here. We can even do some stuff like we can create something called I don't really want to do that with this antenna. I was going to create like segments per meter, but I don't think we want to do that at this point, though we could, I suppose. I think it'll just make things unnecessarily complicated. So now we're defining this in terms of a length, and notice if we zoom out here, if we go back here and change the length from 1 meter to 2 meters, then this line, when we go back here, is going to change correspondingly. So now we'll go back length of 1 meter. Okay, so we have a variable now we can use to change this, and there's a good reason why we want that, because we can use that for the optimizer, which I'll show you later. But for now, let's turn this into a copper wire. The way we do that is with a load. So we're going to add a load called wire conductor. It's tag number 1. First segment is 1, last segment is 19, so we have 19 segments, and then there's a menu here for the conductors that'll insert a conductance value. So I'll put in, we've got like silver, copper, aluminum, brass, or whatever. I'll put in copper, and I'll hit save. Now let's see how that affected things. Let's run our frequency sweep again. Far field pattern. No, we want frequency sweep 140 to 150. And yeah, okay. So generate. This thing's going to pop up again. Alright, so I don't remember. I should have saved a copy of our last graph so we could compare it better. But let's see. Let's check impedance. So it did actually. I think it did actually reduce the resonant frequency a little bit. It made a little bit of difference. But now let's say we really want to get this 146. We really want it to be resonant on this 146 so that this SWR curve will be more centered over here, because if I remember correctly, it's 144 to 148 that where is the VHF band, at least in the US. So we really want to move this thing over. Now we could do this by, there's a way to, I mean, you know, we could just, for something this simple, we could just calculate this out and figure out the length that we need. Obviously, we're going to have to like shorten it a bit to get it resonant at a higher frequency, and we could just calculate that based on like whatever the wavelength is for 146. You know, we could take half of this. In fact, the thing's already calculated it for us. We could just take half of this wavelength number, put it in there, and maybe try to figure out the velocity factor for the copper or something, and then adjust it by that much or whatever. But just for the sake of learning how to use the optimizer, let's use the optimizer to figure out what this length should be. So the first thing we have to do to use the optimizer is we have to do what I just did, and we have to define all of the wires that we want to have the optimizer fiddle with in terms of a variable. We've got to have a variable for the optimizer to play with. So this has been saved. I'm going to save it. And then I'm going to go up here, calculate start optimizer. Okay, now this is the optimizer. Now, in a more complicated design, you'd probably have several variables over here. But what we do is we're going to tell it to take this variable. Right now it's not selected. If I click on it, it moves over into the selected, or it shows up in the selected list over here. And I'm just going to say, right now, these 100s, these are like weights for these different things that could be optimized for. There's SWR, there's gain, there's front to back ratio. I'm actually not sure what FR is. Front to rear, maybe. I'm not sure. I'd have to look that up. Anyway, there's impedance, real impedance in, and reactance at the feed point. So by default, with 100 here, this means it's going to spend all its effort trying to optimize for reactance. If we want, we can tell it to also do SWR. So like 100 here means spend about as much time on SWR as you do trying to minimize reactance. And EFF also is efficiency, so you can also try to optimize on that. But as long as we have a variable selected and we've got some things up here that we want to optimize for, if we want, we could type in like 50 right here, and it would spend less effort. It would give less weight to whether this was correct, but I'm just going to tell it give equal weight to those two things and find a happy medium. Now we've got the frequency we want it to optimize for, so we want to check this and make sure that it's there. And then once we've got that, we hit start. And what each of these little things is, it running the program over and over again. And what it's figured out is, so let's see, it took this is such a simple antenna, it can do it very quickly. But what this is showing is that these are all the different values it tried. So it started with the value of 1, then it tried raising it a little, then it tried lowering it. It like messed with it. This is the thing that tells you whether it how much it thinks the change it made, how much of an effect the change it made had. And then this is all the SWR, gain, front, back, etc., impedance, reactance, efficiency, whatnot, that it ended up calculating for each of these steps. So some of its steps, it the SWR was 6, so it said that was no good, and then eventually it decided that the best it could do was 1.4. What is that? 1.4494. So about 1.45 was the best it could do with this particular scenario, since the only thing it's allowed to do is change the length of the dipole. We haven't given it a way to like change the feed point or do anything else, because only the variables that are selected over here are things that would get to deal with. Now that it's calculated this value, the file still hasn't been updated yet, so we have to click this update NEC file, and it should default to the same file name, 2 meter tutorial NEC. We hit save, and yes, we want to replace it. And now when we close this and open this up again, edit input file, now what we should see that our length variable is 0.98, so it's basically 98 centimeters and 8 millimeters or something, or 8 or 9 millimeters, something like that. So now if we run the frequency sweep again, frequency sweep, we got all our values from last time, everything looks good. Nope. That's weird. Why don't we, why, oh, there it is. It's hidden back there. Alright. So now that we've got this frequency sweep here, we see that it, now we do have it centered on 146 to 148. 146 is like basically the bottom of this curve. And so it's effectively calculated out what we want for this particular scenario. Now we'll get a little bit more complicated, and we'll add another wire to make a cardioid antenna. I'll just go ahead and close this. So a cardioid antenna is kind of like a Yagi, except the only thing it has is one reflector and no directors. It has a reflector, the driven element, and no reflectors. So we've only got to add one wire to do that. So I'm going to add another variable called dir space for director spacing, and we'll use like we can also calculate things out here. So we could set this up as like length divided by 4 or something like that, but we don't really want to do that because I'll show you why. If you have a formula typed in here like length divided by 4, the optimizer will not be able to operate on this director space thing. So what I'm going to do is I'm just going to hard code a value in here. I think what we want is probably something like I'm just going to say 0.25, and then for the comment, it's always good to use a comment here so you don't forget what these variables you're doing are for. So here I'm going to say spacing between director and driven element. Now, because we're going to have more than one length here, I'm going to name this DE-len for driven element length, and then here, actually not director. This is actually a reflector, not a director. Between reflector and driven, I'll just name it R space. So that's the spacing between reflector and driven. And then I'm going to set up R-len for the length of the reflector, and I'm just going to set this. The reflector just needs to be about 10% longer. To be a reflector, something's got to be a little bit longer than the driven element, or it's got to be a little bit longer than resonant, actually. So ideally, our driven element's resonant or close to it, and or very close to it, and the reflector needs to be like a little, not too much longer, but still somewhat significantly longer. So I'm going to put 1.1 meter as the length of our reflector. Okay, so now let's define the geometry for this new wire. We need another wire. This is kind of an annoying bug in this thing where it hides the row on you. Okay, wire. Tag 2. This one's also going to have 19 segments just for the heck of it. One thing you'll figure out about segments is you can't have the segments in your model can't differ too much. Like you can't have one big wire that's one segment and then another wire of the same size with lots of little segments. You need to keep all your segments about the same size, or you'll start to get warnings and errors and stuff that starts to mess up the mathematical model in the thing. Okay, so we're going to take this, nope, it's complaining because I haven't, let me fix that real quick. It's complaining because it doesn't know what len is. DE-len, driven element length. Okay. Alright, so I'm going to make it so that, oh, now what's it complaining about? Oh, I haven't finished my other. Usually you want to get this working or get this completely filled out before you click on this window. It'll give you errors as it tries to like render it in here. What I was going to show you is Y is going to be the forward direction, so I'm going to put the reflector at -Y. So X is still going to be 0. Y is going to be -R space. I think that's what I named it, isn't it? R space, yeah, okay. And then Z is going to be negative R ln divided by 2. And then X, the second X is going to be 0. This is also going to be negative R space. And then this one's going to be positive R ln divided by 2. And we'll just say this is also 20 gauge wire or whatever. Now let's make these thicker. Let's say let's make them like 4 gauge wire just for the heck of it, because these are short. We can use 4 gauge wire for this. Yeah, so that should be what I want, I think. Let's click over here and see. Yep, that's exactly what I wanted. So I've got one element that's DE ln long, centered on the origin here, and then I've got another wire that's a little bit bigger than, that's R ln long, which R ln is set to a little bit bigger, and then between these two is R spacing. Now, because we set this up this way, we can have the optimizer fiddle with all of this stuff. So that's one nice thing. Now here's another. Let's go ahead and turn on the ground, and I'll show you how we can raise this thing up. There's actually more than one way to do it. So let's see. Right now we've got free space. Let's set up real ground. I'll put ground as average. These are different conductivities for the actual soil or whatever under the thing. So notice it's got stuff like moderate, average, good, dry, sandy, coastal, medium, hills, rocky, mountainous. All of these things are different, like they're freshwater, seawater. All of these are different like conductivities for different types of Earth's surface, but I'm just going to make it average. And there's also some other stuff like this use second ground. You could I don't know exactly how second grounds work, honestly. I have not messed with using a second ground. I'm not really sure what it is. Maybe this is if you have like a lake and you want the bottom of the lake to be one type of ground and the surface to be fresh water or something like that. I don't really know. Okay, so now we've got this kind of ground. I'm going to go ahead and save this. Now we'll see this plane appear. Notice that our antenna is stuck in the ground, so we need to move this up. So I'm going to go to geometry, and this time, well, let's see. So we need another symbol. I want a symbol that'll represent the height of the center of this antenna above the ground. And we'll put it at, let's see, we'll just put it at like, we'll put it at 2.5 meters. Notice that's the center. This center is going to be 2.5 meters up, not the one of these, because it's our center's fairly well defined, whereas here we've kind of like got different things that we could start from. So we'll just use the center, and we'll say, all right, the center of this element's going to be 2.5 up. So what we can do is there's this thing that says copy move, and we can tell it T increment is 0. That tells us we're not going to copy. It tells us we're just going to move what we already have. New, I'm not sure what new STR is. Okay, number of new structures to be generated, 0 for move only. Tag number for moved copied structures, that's 0. So okay, number of new. So we do have a nice helpful thing up here that tells us what these fields are I always forget about that. So 0 is move only. We just want to move this stuff. So we can rotate it. We don't want to rotate it through X, Y, or Z. We don't want to move it X. We don't want to move it Y. We want to move it Z. And we want to move it up height meters. From tag, it says start of wire set. We want it, 1 is the first wire. We want both of these, and it says start of the wire set, so we want it tag 1. Now if we go back over here, I'm going to have to zoom out again, page down, page down. There we go. Now our antenna is way up here. Now the other thing we need to do, because we added another wire, wire 2, source load, we also need to make this other thing made out of turn this other thing into a copper wire. So tag number 2, first segment 1, last segment 19, copper. So we've got tag 1 and tag 2, segments 1 through 19 are copper. If we added more segments or removed segments, we'd have to change this thing. But this is a good reason why we might want to use a variable. Let's use a variable for number of segments. Segments equals 19. I'll make this a little smaller. Segs. Someone say something in chat just so I know that somebody's still listening there. Anyway, segs 19. So we can replace this with segs and this with segs. And then we can go over here and replace this with segs. Replace this with segs. Yeah, I mean everything's still transmitting here. Just haven't seen anything from anyone in chat, so I don't know if anyone's still paying attention. Okay. Well, I decided I was going to do this even if there was only one person, so if there's anyone else there, maybe they just didn't sign up for a Twitch account or something, but they're still watching. Anyway, okay, so we've got, both of these are copper. They're both 4-gauge wire. Notice these columns mean different things depending on which thing is selected. So this copy move operation here has got like totally different definitions than the wire thing. So this number 4 is actually, this is something we could actually build. This is uninsulated number 4 copper wire of the sort you could get from like the hardware store as like grounding wire or something. Alright, I'll go ahead and save this. Now let's try a far field pattern calculation. Far field pattern 146. Full pattern generate. This thing pops up again and goes away. And there we go. Let's look at it in the 3D viewer though. I'll show both horizontal, vertical. Okay, so that's what the wireframe looks like. Actually, I thought I had this. I think I may have put this in the wrong. I think it made with a cardioid. I thought this was supposed to give us a cardioid pattern. I must not know what a cardioid is or something. Anyway, but we can see that this is acting as a reflector. Though we can run the optimizer on the length of the reflector to try to maximize the front to back ratio if we want. So that's one thing we could do. Anyway, let's look at it in the 3D viewer. Now notice when we have a ground, the 3D viewer actually will... actually, I think I meant to point this in the X direction. Yeah, I did. X is going to be... I usually do forward in the X direction, not the Y direction. Let me fix that real quick. It's pretty easy to fix. So we want this thing to be, instead of negative Y R space, we want it to be negative X R space, and we want the same thing here. What else am I missing? I think that's it. Yeah, okay. Now we've got the thing pointing. Yeah, okay. Maybe a cardioid's actually a dipole with a one director in front of it. I can't remember, but I know we're supposed to do something. Ah, well, it doesn't really matter. I just wanted to do something a little more complicated than one wire to give you some idea what we can do with this. So yeah, let me just run this again. Oh, if it says screen data used, that means you forgot to save the file. I always save it just to make sure. It'll try to run it with the data in memory. So save the file. NEC output data. Far field pattern, blah blah blah. Generate. Load up the 3D viewer. We'll tell it we want to see multicolor. And we'll get a little thing down here showing that we're getting gain. The reflector is actually reflecting, and we're actually getting gain in this direction. Now we can, if we do zoom, it's actually just going to make this thing bigger, and we can use the left mouse button to rotate this thing, and we can use the right mouse button to move our point, our camera. So I'll rotate it down, move the camera, rotate it back up. Anyway, this will show us the true radius of the wires instead of a, so the wires are a little bit thinner than, it makes it a little harder to see in this case if we do true radius, because our wires are really thin and we're kind of far away from them. So we'll just use the fake radius to make them bigger, easier to see. There's some other things we can do here. Structure, hide structural, hide the antenna. We can show the segments. Let's move back over here. This is a little bit awkward, but anyway, so that shows you the individual segments. That'll show you the current. So the current, if you might remember if you ever studied for the extra, that the current's always highest in the middle and lowest on the end. So that's basically what this is showing us. In this case, it's pretty obvious what the currents are going to be, but you can visualize that on here. Open ends just marks the open ends with a red thing. Anyway, there's some stuff in here you can mess with. So now let me get to the optimizer, since we've got a real use case here. For the optimizer, let's tell it that we want settings. Okay, before you start the optimizer, you always have to save and close that editor. Start optimizer, and then let's see, we'll tell it to optimize R space, the spacing of the reflector, and the length of the reflector. And we'll tell it that we want to optimize the front and back ratio and the SWR and the resonance. So this is theta phi. I think this is what we want, 90-90. Yeah, that sounds right. I guess we'll find out pretty quick if it's not. And then our frequency is correct, so we'll start this up. Now this goes pretty fast when you only have like one or two wires and only one or two variables, but it can really slow down on you. It can really slow down on you if you have a more complicated antenna like a Yagi. It's still calculating, it's still churning away, trying to find the optimal spacing and length of this reflector. Sometimes this could take a while because we asked it to try to get the best SWR, but also try to optimize the front to back ratio. I don't think it's doing much good with the front to back ratio though. That's all about the same no matter what it tries to do. It looks like the SWR is just getting worse. So let's add the driven element length in there as well, and give it all three of those to play with. We'll just tell it to forget the front to back ratio and just go for SWR and reactance. Resume. Now this will go much faster. And it'll actually be able to, now notice our front, no, that's not the front to rear ratio. It's not even calculating the front to back ratio since we didn't tell it to do that. Alright, so that's pretty good actually. It got an impedance of like almost 50 and almost 0 for reactance. And the SWR is like almost 1. Yeah, okay, let's go with that. Update NEC file. Alright, so save that, close it. Okay, so that may be what I had wrong. It actually figured out it's the driven element. It's better to have the driven element longer and have a director instead of a reflector. So let me do something real quick so that this is pointing the right way. Edit input. I'm going to change this to R space instead of negative R space. So it goes in front of it goes toward the x-axis, not backwards on the x-axis. That should give us the same thing. So now let's run a frequency sweep. NEC output data, frequency sweep, blah blah blah, 140 to 150 step 0.01. Okay, same thing as before. It generally remembers your settings. This is going to take a little while. There we go. So yeah, so because we added this other thing, that gave us some more ways to like eliminate the extra inductance or whatever, and now we theoretically could get an almost 1 SWR at 146 and something very low at 148 and 144. Let's see what our far field pattern looks like. Impedance. Yeah, so this really evens out the impedance quite a bit. 50. Reactance is almost 0 at 146. Yeah, so the optimizer did its job. 19 segments. Not really. I mean, you don't want the segments to be too large because you might want to try to calculate an offset feed point or something. Like if you wanted to put the feed point in the center, something like 19 is actually a pretty small number. If we go up here, somewhere here, something about auto segmentation. So see, segments per half wave, it defaults to 20 if you use auto segmentation, so 19 is about what it would default to, and this is a relatively low value. If you wanted to try to calculate an offset feed point or something, one that's not right in the middle, and you wanted to set it wanted the feed point accuracy to be as accurate as possible, then you'd probably want to use a lot more segments. But you know, something like 20 per half wavelength is kind of normal. Is just kind of normal. If there is a problem with segments that are too short, if they're shorter, if the segment is like, if the ratio of the radius of the wire to the segment length is too small, you know, like if the segment is only is as long as its own diameter or something, if you have like end up with like a squat cylinder. Yeah, well, the reason for the centered feed point is just using an odd number. Any odd number you could get a centered feed point, but I don't know. I mean, I could have used 9 segments for this probably, but just because we were going to do something a little more complicated, I decided to use more segments. Sometimes the accuracy is affected by having segments that are either too small or too large. I just kind of knew this was a normal number of segments to have per half wavelength, and I used an odd number so we could put one in the center. So anyway, let me run the radiation pattern thing real quick here. NEC output, far field pattern, generate. And let's look at the 3D viewer. We always have to show the pattern every time. It pretty much looks the same. Yeah, pretty much looks the same. We didn't really improve the front to back ratio or anything like that, but you can see that just adding something like a director or reflector can change the feed point impedance quite a bit. Yeah, you don't want the tune. Yeah, you don't want. It'll start to warn you before you get to the tuna can point. You may only have to get to the like Coke can ratio before it starts complaining. But if you really mess with this, then you'll probably end up getting frustrated at some point because your segments are like too large, and then you try to fix that, and then they end up too small or something. The thing is kind of picky on the segments, so using the auto segmentation thing might be a good feature. I just haven't used that too much. So I guess that's all I really wanted to show anybody today for this. If anyone's got any other questions or anything, yeah, I mean, I guess just ask away whatever questions you've got. Other questions. I think maybe KC1AWV is the only one that's actually logged into Twitch, because I haven't seen anybody else in the chat thing. Okay. Okay, thanks. Yeah. Alright, I will stop my recording then.